For centuries, humanity looked out at the horizon and wondered exactly how large our planet was. The ancient Greeks laid the groundwork for answering this question, with scholars like Eratosthenes developing early methods to estimate the Earth's circumference. This diagram shows the mechanics of his approach. By observing the sun's rays hitting obelisks in two different cities at the exact same time of day, he could measure the slight difference in the angles of their shadows. But the Greek method relied on a difficult logistical requirement. It required a surveyor to physically walk the massive overland distance between those two cities to complete the calculation. Surveyors had to navigate uneven terrain and physical obstacles. Every detour and instance of human error introduced significant margins of uncertainty into the final measurement. Achieving planetary accuracy required a different approach. Someone had to figure out how to calculate the Earth's size without the need for massive surveying expeditions. By the 11th century, Islamic Golden Age, the need for precision had grown. Accurate coordinates were now essential for cartography, navigation, and determining the direction of the Qibla from distant lands. Abu Rayhan Al-Biruni lived much of his life as a displaced political prisoner. This status limited his mobility and his resources as he traveled through the rugged landscapes of modern-day Pakistan. Without the freedom to organize large-scale expeditions, he was confined to the local area surrounding the Nandana fort. But he brought with him a mastery of a new branch of advanced Indian and Arabic trigonometry. These limitations dictated his innovation. Al-Biruni realized that the specific height and angles of a local mountain could serve as a geometric proxy for the dimensions of the entire globe. The first requirement of Al-Biruni's proof was to determine the precise height of the mountain, and he needed to do it without climbing to the summit with a measuring line. He started by establishing a flat baseline on the plains below. Standing at his starting point, he used an astrolabe, a sophisticated observational instrument, to measure the exact angle from the ground up to the mountain's peak. In this geometric model, he walked a known distance backward and took a second angle measurement to the same peak. With these three variables, the two angles and the baseline distance, he used trigonometric formulas to calculate the exact mountain height. Solving this local triangle, Al-Biruni locked in the vertical scale he needed for his planetary equation. With the height secured, he hiked to the summit. From this height, the Earth's curvature becomes a measurable factor. The true horizon actually falls slightly below a perfectly flat horizontal sightline. Using a plumb line to establish a true vertical, he was able to measure the exact angle at which the Earth dropped away, a metric known as the dip angle. This gave him the geometric framework he needed. Al-Biruni connected 3 points in space: his eye on the mountain, the distant horizon, and the absolute center of the Earth. Within this conceptual triangle, he placed his two variables: the mountain height he calculated on the plains, and the horizon dip angle he measured at the summit. This formula bridges those local measurements to the size of the planet. By multiplying the mountain height by the cosine of the dip angle and dividing that by 1 minus the cosine of the dip angle, he isolated the radius of the Earth. His final calculation yielded a radius of 6,339 kilometers. While atmospheric refraction can slightly interfere with visual measurements, his underlying geometric logic was sound, yielding a result within 1% of what we measure with modern satellites today. Through pure mathematical reasoning, Al-Biruni successfully collapsed the scale of the entire planet into a single line of sight. While the Greeks provided the geometric theory, Al-Biruni introduced a new level of verification. He established protocols for instrumental calibration and measurement error analysis that were largely absent from earlier philosophical works. This Khwarizmian approach required that every physical observation be verified through mathematical modeling and peer validation before it could be accepted as truth. He applied this same rigor to larger scales, organizing a project to determine the longitudinal distance between Baghdad and his home in Khwarezm. To measure this 1,500-kilometer span, he coordinated with a colleague in a different city to observe the exact same lunar eclipse. By comparing the local time each of them recorded the event, they synchronized their positions in time and space. By integrating systematic verification with physical observation, Al-Biruni demonstrated that human ingenuity can measure the vastness of the universe from a single point of view.